Welcome to homework.
We are given sets of pairs of integers, and we are asked to determine which of these are partitions of the set Z cross Z. So in part A, we are given the set of pairs XY, where X or Y is odd, the set of pairs XY, where X is even, and the set of pairs XY, where Y is even. We have that, in fact, this collection is not a partition. And to see why, notice that the subsets aren't disjoint. So consider, for example, 0, 0. We have that 0 is even and 0 is odd. I'm sorry, 0 is even. So 0, 0 belongs to two different sets, and therefore the collection is not a partition of Z cross Z. Now in part B, we're given the collection of sets, including the set of pairs XY, where both X and Y are odd, the set of pairs XY where exactly one of X and Y is odd, and the set of pairs XY where both X and Y are even. This is a partition. So we have that a pair XY has to be such that X and Y are odd or exactly exactly one of X and Y is odd, or none of X and Y are odd. In other words, X and Y are even. So it follows that this is a partition. In part C, we are given the collection of sets, which consists of the set of pairs XY where X is positive, the set of pairs XY where Y is positive, and the set of pairs XY where both X and Y are negative. So this is actually not a partition. We have that, for example, consider ordered pair 1, 1. 1 is greater than 0, so clearly 1 is positive. So it follows that ordered pair 1, 1 belongs to the first two sets in the collection. It has both a positive X and a positive Y coordinate. So this is not a partition because the sets are not mutually exclusive. In part D, we are given the collection, which is the set of pairs XY, where 3 divides X and 3 divides Y, the set of pairs XY, where 3 divides X and 3 does not divide Y, the set of pairs XY, where 3 divides X and 3 does not divide X and 3 divides Y, and the set of pairs XY, where 3 does not divide X and 3 does not divide Y. We have that this is, in fact, a subset, a partition, and to see why, well, we have that a pair x, y is such that either x divides 3 or x does not divide 3, and y divides 3 or y does not divide 3. Should be either y divides 3 or y not divide 3. So if we have that x divides 3, or sorry, this should be the other way around. Instead of x divides 3, if 3 divides x and we have that 3 divides y, then clearly it cannot be that 3 does not divide x or that 3 does not divide y. We have that if 3 divides x and 3 does not divide y, it cannot be that 3 does not divide x and 3 divides y. And we can do this and so on. This shows that each of these sets in the collection are mutually exclusive and they cover all possibilities, so it follows that this is a partition. In part E, we're given the collection of sets, the set of pairs xy, where x is greater than 0 and y is greater than 0. The set of pairs xy, where x is greater than 0 and y is less than or equal to 0. The set of pairs xy, where x is less than or equal to 0 and y is greater than 0. And the set of pairs xy, where x is less than or equal to 0 and y is less than or equal to 0. We have that this is, in fact, a partition. So to see why, we have that sets in each of these collection are non-empty. For example, for the set where x is greater than 0 and y is greater than 0, take x and y to be 1. We also have that they are exclusive. So they are disjoint. For example, we have that if x is greater than 0 and y is greater than 0, it cannot be the case that x is greater than 0 and y is less than or equal to 0. It can also not be the case that x is less than or equal to 0 and y is greater than 0. It also cannot be the case that x is less than or equal to 0 and y is less than or equal to 0. So that means they're disjoint. You can do this for the rest of the sets in the collection if you'd like. And we have that it's exhaustive in the sense that every ordered pair falls in one of these sets. So if you have an ordered pair, simply look to determine if the first coordinate is strictly greater than 0 or not. And then look at the second coordinate and determine if it's strictly greater than 0 or not. If both are strictly greater than 0, it's in the first set. If x is strictly greater than 0 and y is less than or equal to 0, it's in the second set, and so on. So it follows that this forms a partition. Finally, in part F, we're given the collection which consists of the sets, including the set of pairs xy, where x and y are non-zero, the set of pairs xy, where x is 0 and y is non-zero, and the set of pairs xy, where both x and y, where x is non-zero and y is equal to 0. We have that this is actually not a partition. To see why, consider the pair 0, 0. Well, in this case, we have the form of an ordered pair where x is equal to 0 and y is equal to 0. So it follows that this ordered pair does not belong to any set in the collection. and therefore the collection is not exhaustive, and so it's not a partition.